The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good morning. It's nice to have a room of people that might be interested in something like this. When you talk about it to normal people, they just kind of stare at you and they say, sure. But now we're talking about cemetery walls so close to Halloween, maybe there is some appropriateness here. As Dr. Kevern says, every time we're talking about pervious concrete these days, it's flat work, it's horizontal, and none of that is reinforced. So reinforcing steel does need to become part of the subject, and rightfully so. And in about late 80s, early 90s, with some of the older guys here might know Albert Litvin, who was a mentor of mine at PCA. We went to this cemetery to take a look at something unrelated to that, to look at the capstones on the pilasters because they were falling or in danger of falling, and there was a safety hazard. That would only be a safety hazard on the live side, not the dead side. And of course, they didn't do anything about it. The cemetery was completely only interested in the economic issues. They wanted to rip it down and put down a wrought iron fence, which they did, and it was corroding within about 10 years. But I noticed that wall at that time, and for the next 20 years, every time I drove by, it could look a little obsessive. I would get out of the car and take pictures, and whatever thing was spalled, I would bring it in, and then the petrographers at the lab, I go, hey, can you do this on the side for me? And I have all this pervious concrete at home, but it's all unauthorized. If I call the cemetery to ask, hey, how old are those walls? They literally think it's like an April Fool's joke and say, are you like Ghostbusters or something? So I don't even really have an actual nailed-down date on the wall, but there's some advertising here that says these dates. So original construction, 1864. I doubt they're filling up the cemetery at that time. Sometime thereafter, the walls will be constructed. I've tried to do some photographic imaging to see if those walls are in place, and it gets very expensive, and you'd have to keep paying for every year you want to look at. So, I mean, if we do it chronologically from today back to 1864, that's 150 years. So I'm saying 100 years is probably a conservative guess that these walls are out there and being durable. I don't want to take a bunch of time. I've only got all qualitative slides here, but when I wrote the paper and Rex Donnelly was reviewing it, he says it's too long. And I said it's kind of like a joke. You have to have the setup before you can say the punchline. And the setup, and I'm not going to belabor this point because everyone knows the corrosion process, but in the paper I talked about the corrosion process and everything we look for in conventional steel and know to be intuitively the right direction. Quality, consolidation intimately around the rebar with this low permeability concrete, which a high pH, the alkalinity, protects the concrete against the carbonation front, and that's how we get our longevity in terms of corrosion durability. So intuitively, this shouldn't work at all. The reason I pulled over, I go, how come that hasn't fallen down 10 years ago like the wrought iron fences, different canary in the tunnel, but the same kind of durability issue. And that's when my interest really started to peak. Again, like I said, the initial issue was the capstones falling, but they kind of dealt with that. They knocked off the loose ones and then just left it before they knocked the whole thing down. And then a little bit of help from ACI staff in some of the initial assumptions. They go, water's going to go right through there anyway, so it should have all kinds of problems from freeze-thaw and corrosion. And Agata Pick found me this article from a 1950 February ACI journal indicating that capillary action into a wall, now they're talking about a rendered wall when you read the bottom of that, it doesn't progress into the wall, maybe 1 or 2 aggregate diameters. So this aggregate was about 3/8 and 5/8 inch chip, so it's comparable to what this is saying here, but it's saying it resists that. It doesn't help promote flow through the wall, even in a horizontal driven rain. The rendering comment is kind of applicable because the bottom portion of the support, let's call it the stem wall or the foundation that this wall sits on, I go, oh, that's conventional concrete. And that's where the drainage party ends. The concrete gets water coming into the wall, comes down vertically, beautifully taking advantage of the 20 to 30% void structure of our Pervious in a way we're not used to seeing it used. And here you get to see where all the hydraulic stuff happens. It's right out in the open. But then there's some probably lingering of the water leaving because it weeps out the bottom, and that's probably the wettest part of the wall, and that's where the damage started to manifest itself first. Manifest itself, again, probably sometime around 100 years later. So intuitively, this shouldn't work. And then this is just assumptions on my head, which Dr. Kevin will talk about later, and some of the work that we may do in the future might bear out. I started to think there's an analogy here to freeze-thaw durability. The air voids there help dissipate the pressure from ice dilation, and here the corrosion product, it's like trying to punch yourself out of a bag that's too big for you. The corrosion products will start to invade the void structure around there, but still that's more time before damage for sufficient pressure to cause falling. I really started getting hyper about looking at these walls a lot more because what's in the background is already them being knocked down and being replaced. And something that's really a historic, dare I say, monument is going to be gone. And I just think that there's something from our forefathers that we can learn. I don't exactly know what it is. I do have one obvious answer, what not to do, but something about this void structure around the reinforcing steel actually has, non-intuitively, has some benefit. Was there? Go ahead.
I think there's probably two things missing that are worth noting, and probably not doesn't have any air entrainment. It probably has no de-icing salts used on it.
We don't have chloride profiles on the wall. However, it is near a street, but that's not a constant situation. Many times, especially on the weekend, there's just cars parked there all the time. Think of that as a shield for the chloride spray from the traffic going on the road. But when it's open like that, yeah, it could get chlorides. No, the paste is not air entrained, but we do. I do have a couple petrography shots. We have a lot more that we don't have time for. Yes, sir.
Quick question, George. Have you actually done any tests to see what the actual voids are in this space?
Just visually, and I'll show you a cross section of a lap section of a sliced piece of core at the end. I've only got 8 slides, so I'm not going to bore you all day here. The assumption that there was concrete that this wall was sitting on wound up being incorrect. It's actually the exact same concrete, only with a 1/4-inch thick mortar parge coat over it, which was interesting, and that lasted so well that some of the new stuff in the background, they just went right on top of it. Now, if I were doing a 100-year-old redo, I would have went and got it all and just been done with it. But it was in such good condition that they stayed with it. They also used that for the wrought iron fence, too, which then you have like a lollipop. You have the reinforcing steel in this store, and it started to blow up. When the parge coat was breached, all hell broke loose because then there was no drainage exit. We're in a bag. You know, we're in a parge coat closed system, totally opposite of what the wall is when it gets done. So you see this the spalling at the bottom, and taking a closer look at it, I mean really bad. It would be to the point where it completely disintegrates. But as you get up above that elevation of the interface between the wall and its foundation, it improved dramatically, and sometimes the twisted bar was completely visible in its original shape. I've got hundreds of pictures of these. I should really take the pictures of the people watching me take the pictures. And not to say that we don't have drawings, nothing like that's available. Estimated spacing about 12 inches on center vertically. I don't have enough spalls to happen, that's a good thing, on the horizontal spacing. But it did occur there too, mostly where it was repaired. Because it was repaired with conventional mortar, which just started to dam up the system and work against what was so beautiful and letting it work to 100 years or so. I just have this one so you can see it because the video is a little fuzzy. It's real short. I'll play it twice if I can. But the video here just is. I just took a pencil and just scratched the, if it plays. Oh, of course not. I set it up before and it played this morning. Sorry, it's not playing. But the point is here, the more they fixed it, the worse it got. The whole wall just started to explode. There were areas that were, it was just so obvious that was, the doctor was the executioner here. And looking for an audience that might be receptive to this in concept alone, I was the dinner speaker in September for I Cry, and I thought this will be fantastic because 522, I was preaching to the choir. They go, "This is fantastic," and I go, "Well, at least they have someone on a kindred level." So I thought maybe I Cry Repair Institute might find it interesting. But since they're knocking it down, and this is not a big money item to them, there was, interesting. Where's the bar? It was. Taking a look at a close-up, the petrographer Ron Sturm, who I worked with for many years at CTL, was very gracious to do some, got a whole bunch of stuff that we can still get from Ron, but the cement paste, surprisingly, was not thoroughly carbonated. Very low water-cement ratio, very low in permeability. It's too old to give you a real estimate without being, from 0 to 1 on water-cement ratio, but it's around the 0.32, 0.38, but it's kind of getting old for that. Great paste aggregate bond, good quality aggregate. Like I said, you can't make up for bad materials. A cross-section, to answer your question, Dale, about how the aggregates look. It's a 3/8, 5/8 chip, nice aggregate coating, 20 to 30% voids, non-Aaron trained. I was waiting for, you'll ask questions. I don't know how it was placed. Obviously, it wasn't pumped. It was way too early, but they did a very nice job. I see they're not really lift lines, they're just form lines. There were no cold joints to say. Your guess is as good as mine how they placed that. I would like to know that. Anywhere from a bucket might have been possible to, I'm really wild here, a wheelbarrow on a ramp dumping it, but it'd have to be almost continuous. But good construction overall, I think.
Do you think it's possible, George, just from the no fines, that they used it as almost a hand pack?
Thank you, Walt. It is not strict no fines. It's about 5% estimate on natural sand.
Did they add it?
Did they, pardon?
That they probably added it? I mean, that's pretty sophisticated, adding such a small amount of sand.
No, it's not. It's not just in one or two. Every single one that we kind of looked at, yeah, there's about a 3 to 5% fines in there. And having done a couple mixes like that too, and starting with nothing fines, and as you start to add a little bit, the strengths pick up nicely before you start clogging things. Yes, sir.
Do you think the repairs were trapping moisture?
Absolutely, no doubt, no whatsoever. That's why I thought maybe I Cry, it's what not to do, but it's start thinking about it would not just be a walk in the park to fix that. I mean, you use bonding agent, how do you chip it out? What's the geometry of that patch? Is it, it's not, you're going to be kind of a form and place behind a form. Is that just pushed in? You can't really vibrate it. There's a lot of things to think about. Would you anchor that patch in there? Or maybe the best thing to do is go straight through the wall and put it a full, I don't know. That would have to be thought out more yet. Yes, sir.
Do you have any idea why they did it this way originally?
It was cheap. It was inexpensive at the time. There was also because Paul Godet has done a lot of this, the 63rd Street Beach. I used him he reviewed my original paper. He's done a lot of stuff on what was done for the World's Fair, and they used this material again then. It's very beautiful to us. It looks very nice when it's new.
We know that if we're going to use 318, we say we want to protect reinforcing steel, we want a low water to cement ratio. This protects our from corrosion, but once corrosion starts, it progresses relatively rapidly. So once it initiates and once it starts to propagate, we get cracks, it splits open, water gets in there, or whatever, and things fall apart quickly. So we said, okay, maybe one of the theories was this has lasted so long is because it hasn't split open. It's corroded in there, but we got a lot of pore space, so it's oozing into the pore space. Hey, maybe that's what we're doing. So we set up this Florida test method. So this is the accelerated Florida test method. This is what we call the lollipop test. So we take some corrosion or some rebar, we stick it in a concrete cylinder. We take that concrete cylinder, we put it in a salt calcium chloride bath, and then we run a current between the solution and the steel to force the chlorides to it. we can proportionally evaluate time to corrosion. Love the test because we get to, you can initiate full corrosion destruction in 2 to 3 weeks. It's a great fun test. So this is kind of what happens is you run a current, and once it passivates, the current drops, and then the second you get some cracking, all of a sudden your current goes up because you're basically mainlining to the steel. And so here we did some 2-layer samples. So we did regular concrete, and then we did one where we had a pervious core, and then we placed conventional around it. And the pervious, we had a real hard time initiating or seeing cracking in those samples. So here's our conventional. You get corrosion. It splits. The corrosion product goes everywhere. Here's the pervious core. We have corrosion. We can see corrosion products kind of bubbling out the top, but we didn't split it. So then we take them and you saw cut them and you say, all right, here's our conventional. It definitely expanded and split. Our pervious, it definitely expanded into those pervious voids. So you say, okay, maybe that's interesting. Let's progress to the next stage. So we're actually doing some ponded corrosion potential testing, long-term testing right now, where we've got, it's a conventional layer of concrete, a layer of pervious with some steel in it, and then a conventional, so it's kind of 2-inch, 2-inch, 2-inch there. We've got a PVC pipe in the top, and then we use that to pond a chloride solution, and then we can measure the corrosion potential of what's happening. So we did kind of a very high porosity coarse pervious. We did kind of a medium porosity 3/8 pervious, and then we did a lower porosity, a sand-only pervious concrete, and then a control. So we got rebar running through the middle of all those samples. You pond chloride solution for 2 weeks. You pour it off. You let it dry out, and you do dry, wet. So kind of worst case scenario for corrosion, and then you test it with linear polarization. The sides are all wrapped in epoxy, so we don't have any moisture movement in or out of it. So it's 1D of diffusion. So we got a whole bunch of samples. We've been running them for a long time now. And so I've got, just to show you what we look at, so we're way out 300 days. We're getting ready. I mean, we've been testing almost a year. But typically what happens is initially you get a spike in current because your steel is passivating. And then once you get that passive coating, then it kind of drops down. And then once corrosion initiates, this is going to spike up to, we say if it's above 1 milliamp, then we have corrosion happening. So here's our high porosity pervious, really low. Here's our conventional. Low porosity pervious, a little bit higher, but still low. And here's our medium pervious, still low. So if we look at those, we haven't initiated corrosion in any of these samples, but we do see that the pervious system has a much lower potential at this point. We've got humidity sensors in there. We've got a much lower humidity in the pervious layer than in the conventional concrete layer. So it's something's happening. So what we're going to do is once we hit a year, we're going to take half of the samples and we're going to induce a voltage or reduce a current through it to try to accelerate and see if we can differentiate between them. So this is special interest. Off the field, we said, hey, let's try some stuff on the side, and we made some lollipop samples, and we said, hey, it seems to help in lollipop samples. We're doing some linear polarization. Seems to be better. We're getting ready before Thanksgiving. We're placing some very large beams, reinforced concrete beams with the 2-layer system, and we're going to break them to look at bonding behavior, but it's kind of a side piece based on what George has shown us. So with that, we are, I'd say we're running just a little bit late on time. So